We flip a switch, the lights come on, we tap our phones, information appears. It's easy to forget that the bedrock of our modern world lies, well, quite literally beneath our feet. Extracting minerals from the earth seems like it should be straightforward, but as we're going to find out, it's anything but.
Indeed. Today we're taking a deep dive into the fascinating and, surprisingly complex world of mineral extraction. Forget simple pickaxes and shovels. This is really a realm of advanced technology, intricate economics, and a deep understanding of our planet.
Exactly. We've gathered a really rich set of sources for you, covering, well, everything from the precise art of drilling deep into the earth and the financial equations that determine if a deposit is actually worth pursuing, to the diverse methods used to unearth these valuable resources.
Right.
The controlled power of blasting, the sophisticated processes of turning raw ore into usable materials, the absolute necessity of mine safety, and, of course, the foundational science of mining geology that underpins it all.
So our mission today is to synthesize all this information, basically pull out the crucial insights, and give you, our listener, a clear, comprehensive understanding of how we get minerals out of the ground.
Yeah, the whole journey.
The whole journey, from those first clues that suggest, something might be there, to the various techniques used to access it, the economic realities that shape the whole operation, and crucially, the considerations for people and the environment.
Okay, so let's get started right at the beginning. The hunt. How do we even begin to pinpoint where these mineral treasures might be hiding? It's not like they're a giant dig here signs, is it?
Not usually, no. The process starts with exploration, and it's kind of like detective work, really. The initial phase, often called prospecting, is all about identifying areas with the potential for valuable mineral deposits.
Right, narrowing it down.
Exactly. Think of it as narrowing down a vast landscape to just a few promising leaves. We generally use two main categories of methods: direct and indirect.
Direct sounds pretty intuitive, like getting out there and actually looking.
Precisely. Direct methods involve physical and geological mapping. So you'd have geologists on the ground, meticulously observing the terrain, identifying different rock types, looking for any surface evidence, outcrops, maybe unusual coloration, even certain plants sometimes.
Oh, really? Plants?
Yeah, some plants can indicate specific minerals in the soil, anything that might suggest mineralization beneath. They're essentially creating a detailed geological picture of the area.
So it's like reading the landscape for clues about what's hidden inside.
Okay.
And then there are the indirect methods, which sound a bit more high-tech.
They generally are. Indirect methods use things like geophysical and geochemical surveys. Geophysical surveys use sophisticated instruments to measure the Earth's physical properties, things like gravity, magnetic fields, electrical conductivity, radioactivity.
How does that help?
Well, anomalies, deviations from the norm in these measurements, can hint at buried mineral deposits that have different physical properties than the surrounding rock. And geochemical surveys involve analyzing the chemical composition of samples, rocks, soils, stream sediments, even that vegetation we mentioned. Unusual concentrations of specific elements can be a strong indicator.
So using both your eyes and scientific instruments to piece together the puzzle, and drilling only comes in after these initial surveys point to a promising area.
Exactly right. Drilling is a significant investment, a big cost. So it's typically done once the initial prospecting has identified specific target areas with a higher probability of containing valuable minerals. Drilling lets us get detailed, first-hand info about what's actually down there.
Right, you need to actually get a sample to know what you're really dealing with. And I remember reading that not every mineral find is created equal. There's a classification system.
That's correct. As exploration progresses and we gather more data, including from drilling mineral finds, get classified based on how much we know and their potential for economic extraction.
Okay.
We start with prospects areas that show geological promise, but, need more investigation. Then we might identify resources, these are known concentrations, with reasonable prospects for eventual economic extraction. Think potentially valuable, but we're not quite sure if we can profitably get them out yet.
Still a bit uncertain.
A bit, yeah. Finally, the ultimate goal is to define ore reserves. These are the parts of a resource that are confirmed to be economically mineable. Detailed studies show profitable extraction is feasible, considering all the technical, economic, and legal factors.
Okay, so they've gone from a hunch, basically, to a confirmed deposit that looks like it could actually pay off. Now comes the drilling itself, and it sounds like there's a surprising variety of ways to do that.
Absolutely. Drilling is crucial not just for exploration to understand the geology and extent of mineralization, but also later for mine development and even production. But as I said, it's a substantial cost. So picking the right drilling technique for the specific situation is really important. In gold fields, for example, which is a pretty common scenario, three main techniques are often used: RAB, RC, and diamond drilling.
Okay, let's drill down into those then. What's our Abbey all about?
RA stands for rotary air blast. It's generally the most cost-effective of the three, the cheapest, which makes it popular for that initial reconnaissance work.
Okay.
But it's also the least penetrative. Typically only reaches depths of around 100 meters, maybe a bit more. It works by using compressed air to rotate a drill bit rapidly, breaking the rock into small fragments cuttings.
And how do you get the samples out?
Those cuttings are then blown up and out of the hole using the same compressed air, traveling in the space between the drill rod and the wall of the borehole. It's a pretty simple single-walled drill pipe system.
So it's quick, doesn't break the bank, but what kind of information do you actually get from it?
Well, ROB drilling mainly gives you samples for geochemical analysis, testing the chemical makeup of the broken rock. It's useful in the early stages for sampling that weathered layer above the fresh rock, the regolith, to see if there are any initial signs of minerals.
So pros.
Yeah.
Cheap, fast, big sample volume.
Right, but the downsides are significant. You generally don't get samples of the fresh, solid rock underneath. The depth is limited. You don't get much structural info about how the rocks are arranged. And there's a risk of the sample being contaminated by stuff falling in from higher up the hole.
Right, okay. So it's a good starting point for a broad sweep, but maybe not for detailed geological understanding. What about RC drilling?
RC means reverse circulation. It's a step up in both cost and capability. It allows for penetration to moderate depths, maybe around 350 meters typically. And a key difference from RB is that RC drilling does provide samples of fresh, unweathered rock.
How does that work differently?
It uses a dual-walled drill pipe. High-pressure fluid, usually compressed air, goes down the outer pipe. The rock chips created by the drill bit are then forced up through the inner pipe. That reverse circulation helps keep the sample cleaner.
Ah, so you get a more representative sample of the actual rock you're interested in. What are the other pros and cons there?
Advantages.
Yeah.
Relatively cheaper and quicker than diamond drilling, and you get a large, fairly uncontaminated sample of fresh rock, which is crucial for accurate analysis.
And the disadvantages?
Well, access can sometimes be limited in really rugged terrain. It still doesn't give you detailed structural information like rock orientation. And contamination can still be an issue if you drill below the water table. Groundwater can mix with the sample.
Okay, so better samples, deeper reach. Then we have diamond drilling. Sounds like the premium option, the gold standard for geological info.
It is indeed the most expensive of the three, yeah. But it allows for the greatest penetration depth, and most importantly, it yields whole rock samples in the form of a core.
A core, like a solid cylinder of the rock.
Exactly.
Yeah.
A solid cylinder showing the rock layers the drill passed through. This gives you the maximum amount of geological information. Geologists can examine the intact structure, identify minerals and their relationships, figure out the orientation of veins, faults, all that crucial stuff.
Wow, okay, so super detailed.
Super detailed. The samples are generally uncontaminated, very high quality. But the significant drawbacks are the cost. It's expensive and it's slow. The core sample diameter is relatively small, and it needs extensive site prep, plus a reliable water supply to cool the bit and flesh out fragments.
Makes sense. You're basically using industrial diamonds to grind through solid rock, so it's going to be a more involved and costly process. Now, you mentioned these are common in gold fields, but there are other drilling methods used in different contexts, right?
Oh, absolutely. There's a whole variety of other techniques, each tailored for specific purposes and ground conditions. Things like air core drilling, cheaper, faster way to sample shallow bedrock. Auger drilling, which uses a big screw, basically, to bring up loose stuff near the surface. Great for soil sampling. Then you have top hammer and down the hole, DTH, drilling. They're percussive methods, good for hard rock.
Like a jackhammer action.
Sort of, yeah. Rotary drilling uses a rotating bit with downward pressure. Pretty versatile. Often uses drilling mud, hence mud rotary drilling, to remove cuttings and stabilize the hole. Air percussion uses compressed air to power a hammer. And even shot hole drilling, which is just small holes for placing explosives.
So it really depends on what you're trying to achieve and the type of ground you're dealing with. Sounds like the choice of drilling method is a very strategic decision.
Precisely. The selection is heavily influenced by the stage of exploration. RB often gets used for that initial broad-scale work. RC is typical for intermediate stages, delineating the ore body, maybe for grade control.
And diamond?
Diamond drilling is usually reserved for the later stages, especially when you need that detailed understanding of the ore body's structure and grade distribution for really accurate mine planning.
Okay, so they've found a promising area, drilled enough to understand what they potentially have. Now comes the big question. Does it actually make economic sense to build a mine? Let's talk about the economics.
Yeah, this is absolutely where geological promise meets financial reality. A mineral deposit, doesn't matter how rich it is, will only become a working mine if the potential revenue from selling those minerals outweighs all the costs of getting them out and processing them, and provides a reasonable return on investment, of course.
Makes sense.
There are basically two main categories of cost factors to think about.
Okay, what's the first big bucket of costs?
The first covers all the actual operational costs, everything needed to run the mine day to day. So labor, miners, engineers, admin, staff, materials consumed, explosives, fuel, lubricants, chemical reagents,
Right.
the capital costs for buying and maintaining equipment, energy costs, which can be huge, especially for deep underground mines needing ventilation and cooling, infrastructure development too, roads, power lines, processing plants, all that stuff.
Right. So all the tangible inputs needed to get the job done.
Got it. And what's the second major factor in the economic equation?
The second critical factor is the price of the actual metal or mineral the mine is producing. This price is set by global supply and demand, and it directly impacts the mine's profitability in a big way.
Because obviously higher prices mean more money coming in, but I recall reading that higher prices can also kind of indirectly affect the costs too. How does that work?
You're right, it's an interesting dynamic. When the market price for a metal goes up significantly, it can suddenly make mining lower-grade deposits, ones with less valuable mineral per ton of rock, economically viable.
Okay, ones they wouldn't have touched before.
Exactly. But this increased mining activity across the industry, chasing these marginal deposits, can actually lead to a rise in the overall cash cost curve for that metal because these operations are often less efficient.
Plus, high metal prices fuel demand for mining inputs, skilled labor, specialized equipment. This increased demand can drive up the prices of those inputs, adding to operating costs for all mines. It's like a boomtown effect, you know?
Yeah.
Everything gets more expensive.
Right, supply and demand for the inputs themselves.
Exactly. And then there are the logistical complexities, maybe higher energy use for lower grade or more remote deposits. It all adds up.
So it's a dynamic relationship where the selling price and the costs of production can influence each other. Now, how do mining companies actually figure out if a project is going to be profitable before they invest, potentially billions? I saw some financial acronyms in our sources.
Yeah, there are several key financial evaluation metrics they use. One of the most fundamental is net present value, or NPV.
NTV. Okay.
Essentially, this calculation projects all the future cash inflows, the money the mine is expected to make, and discounts them back to their value today, accounting for the time value of money and risk. Then it subtracts the present-day value of all the outflows, initial investment, ongoing costs.
And you want that number to be?
Positive. A positive NPV generally indicates a project is expected to generate more value than it costs, exceeding the required rate of return. It suggests profitability.
Okay, that makes sense. You want the present value of future earnings to outweigh your present costs. What about those other acronyms I saw? ROM, IRR.
Right. Another one is return of margin, or ROM, sometimes called gross margin, return on investment, GMROI. This focuses on the gross profit relative to the capital invested, gives you an idea of the efficiency of the investment in generating profit from sales.
Okay.
Then there's the internal rate of return, or IRR. This is the discount rate where the NPV actually equals zero. It basically represents the effective rate of return the project is expected to yield. Generally, a higher IRR suggests greater potential profit compared to the investment and the cost of capital.
Higher return rate. Got it.
And finally, there's a simpler return on investment, ROI. Measures profitability by dividing the net profit by the initial investment, usually as a percentage. Straightforward measure of how effectively the capital is generating profit.
So they're looking at a whole range of financial indicators to get a comprehensive picture. I also noticed some trade terms mentioned: FOR, FOB, CIF. How do those fit into the economic picture?
Oh yes, those are crucial for the logistics costs getting the stuff to market. Free on rail, FOR, means the seller pays to get the goods onto a train car, but the buyer takes over costs and risks from there.
Okay.
Free on board, FOB, is more general. It defines when responsibility transfers. FOB shipping point means the buyer takes over as soon as it leaves the seller. FOB destination means the seller is responsible until it arrives.
And CIF.
Cost, insurance, and freight, CIF, is for sea shipments. The seller pays transport costs and insurance to the destination port.
Oh.
These terms clearly define who pays for what and who bears the risk during transport, which directly impacts the overall economics.
Right, it's all part of calculating that final bottom line. And our sources also highlighted the really significant role the mineral industry plays in a nation's overall economic health.
Oh, absolutely. Natural resources, especially minerals, are often major contributors to a country's economic development and its GDP, its gross domestic product. A thriving mining sector can generate huge revenues, create jobs, stimulate regional development, provide essential raw materials for other industries. It plays a vital role in upgrading the national economy.
Okay, so assuming the numbers add up, the geology looks good, the economics work out, how do they actually get these resources out? I know there are different approaches depending on how deep they are.
That's the fundamental distinction, yeah. Surface mining versus subsurface, or underground mining. Surface methods are for deposits relatively close to the surface. Subsurface is for the deeper stuff.
And surface mining is more common.
Currently, yes. It accounts for over 2/3 of the world's total annual mineral production, largely because it's generally cheaper and more productive than underground methods, when it's applicable, of course.
Right. Let's start with surface mining then. What are the typical steps involved in getting a surface mine up and running?
It usually starts with thorough site preparation, clearing vegetation, removing topsoil, hopefully saving it for later reclamation.
Good point.
Then a crucial step is dewatering, getting rid of any groundwater in the area and stopping more from flowing in. Then you need access building roads for heavy equipment, personnel. And finally, the really big job in surface mining, removing the overburden.
That's the rock and soil on top of the valuable stuff.
Exactly. The layer covering the mineral deposit. It involves drilling and blasting or using massive excavators and loaders to break it up, then hauling it away to waste storage areas.
And within surface mining itself, there are different techniques depending on the deposit.
Correct. The main mechanical methods are open pit mining and strip mining. Those are the most common. But there are also more specialized techniques like mountaintop removal, terrace mining, and quarrying.
Open pit mining, that's probably the image most people have, right? These massive step piles in the ground.
That's a very good visual, yeah. Open pit mines are used for near-surface deposits where the overburden isn't too thick compared to the ore body. Mining happens in a series of benches, horizontal steps, or levels in the pit.
Why? Steps.
Stability. The benches can be anywhere from, say, 4 to 60 meters high, depending on the equipment. The pit walls aren't vertical. They're stepped, with inclined sections called batters and the flat working areas of the benches. This stepped design stops large rockfalls, and haul roads are built along the side, like a ramp system, so huge trucks can drive ore and waste out.
These open pits can become absolutely enormous. What are some of the key environmental things to think about with them?
Well, they can have significant environmental consequences, no doubt. Large-scale removal of soil, vegetation means habitat loss, impacts on biodiversity. The process generates a lot of dust, affecting air quality.
Right.
And exposing previously buried rock to air and water can lead to acid mine drainage if sulfide minerals are present. Toxic groundwater can also sometimes accumulate at the bottom if it's not managed properly.
Okay. Then there's strip mining. I understand that's often used for flatter deposits, like coal seams near the surface.
That's correct. Strip mining is particularly well suited for those relatively near surface, sort of tabular or seam-like deposits. Coal and lignite are the most common. You remove a long, continuous strip of the overburden to expose the mineral seam underneath.
Sounds efficient.
It can be. Because the ore body is close to the surface and often horizontal, strip mining can use some of the biggest earth-moving machines on the planet. Huge drag lines, bucket wheel excavators.
How does the actual process work? Do they just keep stripping?
There are two main variations. Area stripping is used on relatively flat terrain. You make a long cut, remove the ore, then make the next parallel cut, and the overburden from that cut often gets dumped into the void left by the previous cut.
Ah, okay, backfilling as you go.
Sort of, yeah. Contour stripping is for hilly or mountainous areas where the seam follows the land's contour. You remove overburden along the contour, creating a bench. Sometimes after contour stripping, they might use auger mining, drilling horizontally into the exposed seam to get more out.
I saw the term stripping ratio related to this. What does that tell us?
The stripping ratio is a critical economic number in strip mining. It's the volume of overburden you need to remove to get a certain amount of ore, usually expressed as cubic meters of overburden per ton of ore.
So like 3.1 means 3 cubic meters of waste for 1 ton of ore.
Exactly. And obviously, a lower stripping ratio is better economically. Less waste to move means lower costs, higher profitability.
Right.
If the ratio is too high, the cost of moving all that waste might make the whole project uneconomic.
Makes perfect sense. You don't want to spend more moving waste than the ore is worth. You also briefly mentioned other surface techniques.
Yeah. Mountaintop removal, a more controversial method, mainly for coal in mountains. They literally remove the mountaintop to get at the seams. The waste rock often goes into adjacent valleys. Huge environmental impact.
Right.
Terrace mining is used when the overburden is too thick to dump directly over the edge, so they use benches that advance sideways. And quarrying is specifically for extracting building materials, stone, gravel, sand.
So what are the overall pros and cons of these surface or open cast methods compared to going underground?
Well, the advantages generally include lower excavation costs, especially when it's shallow. It's usually safer than underground environments. Easier overburden removal, no need for complex ventilation systems, often a quicker return on investment.
But the downsides.
Also significant. Surface mining can cause substantial environmental pollution, land degradation, water contamination, air and noise pollution, deforestation, habitat loss. It's also very weather dependent. And this becomes uneconomic if the deposit is too deep or underpopulated areas.
Okay, so those are the main mechanical methods at the surface. What about those aqueous excavation techniques you mentioned, using water?
Right. Aqueous methods use water or other liquids. The main types are placer mining, in situ leaching or solution mining, and undersea or ocean mining.
Placer mining, that makes me think of the old gold rushes, panning in rivers. Is that still a thing?
Yes, placer mining is still practiced, though often with more mechanization now. It's used to extract heavy, valuable minerals, gold, tin, platinum, diamonds, gemstones that have been naturally concentrated in loose deposits like gravels and sands, usually by water action.
How do they do it now?
Methods range from simple stuff like hydraulic mining, using high-pressure water jets to erode deposits, to more complex operations like dredging for underwater deposits. Sluicing uses channels where water flow separates heavier minerals.
And where do you find these placer deposits?
Typically where water velocity slows down, allowing heavier particles to settle. Bends and rivers, behind rocks, downstream areas.
Fascinating how nature does the concentrating first. What about in situ leaching?
In situ leaching, or solution mining, extracts soluble minerals from deep underground without digging up the ore. You inject a leaching solution of lixiviant into the ore body through boreholes.
And it dissolves the valuable stuff.
Exactly, it dissolves the target minerals. Then the mineral-rich solution is pumped back to the surface through other boreholes for processing. It's used for salts, lithium, potash, copper, uranium, things that dissolve easily in porous rock.
Advantages, disadvantages.
Generally lower environmental impact on the surface, less disturbance, but there's a risk of the leaching solution which might contain acids or heavy metals leaking into the surrounding environment. Needs careful management. Often used for evaporate deposits.
Okay. Sounds targeted, less messy on top. And finally, undersea or ocean mining, is that viable?
Well, minerals are present in seawater, but usually in concentrations too low to make deep ocean extraction economic with current tech. Mining the continental shelf, the submerged edge of continents, is more feasible for things like sulfur, phosphate, some metals.
But it's not common.
No, it's still very expensive, technically challenging, and has significant environmental considerations to manage.
Okay, so that gives us a good handle on getting minerals near the surface. What happens when the valuable deposits are much deeper underground? That's where subsurface mining comes in, right?
Exactly. Underground mining is for deposits deep below the surface, where removing all the overlying rock just isn't practical or economic. The specific method chosen depends heavily on the ore body, its shape, size, thickness, dip, and also the strength of the surrounding rock.
And it gets tougher the deeper you go.
Definitely. Pressure from the overlying rock increases dramatically. In very deep mines, this intense pressure can cause dangerous rock bursts, sudden violent fracturing of the rock around the openings.
Yikes, that sounds incredibly dangerous. What's the general sequence of activities in underground mining? Like this cycle?
A typical cycle starts with drilling a pattern of boreholes into the rock face. Then, those holes are charged with explosives. Everyone clears out, the explosives are detonated to break the rock.
Then you gotta get the broken rock out.
Right, that's mucking. Removing the blasted rock, or ore. After mucking comes scaling, carefully removing any loose, unstable rock from the walls and roof to prevent rock falls. And finally, installing ground support systems, bolts, mesh, concrete to keep the opening safe and stable long-term.
And when would you typically choose underground mining over surface methods?
Generally, when the ore deposit is deep, or if it has a steep dip or inclination making surface mining difficult, or if the concentration of the valuable mineral is high enough to justify the higher operating costs of going underground.
Just like surface mining, I guess there are different underground techniques, too.
Oh, yes. Broadly categorized by how much support they need. Supporting methods like cut and fill, stole stopping, square set stopping, use artificial support backfill, timber structures, especially where the rock is weak.
Filling the void as you go.
Often, yeah. Unsupported methods like some types of stopping and sublevel stopping rely mostly on the natural strength of the surrounding rock, used in more stable rock formations.
And
Caving methods, like block caving, are large-scale techniques for massive ore bodies. You basically undercut the ore and let the overlying rock collapse in a controlled way as you draw the ore out from below. Stopping in general just means excavating the ore body itself to create openings. You develop access tunnels, called drifts, and then create the stopes where the ore is extracted. Shafts go down from the surface and levels branch off horizontally.
block caving sounds intense. Intentionally collapsing the rock above you.
It's highly efficient for very large, relatively low-grade ore bodies that tend to fracture easily. By undercutting and drawing ore from below, the block collapses under its own weight. Minimizes drilling and blasting of the ore itself, but needs meticulous planning and strong support in the extraction areas. You have to really understand how the rock will behave.
Okay, so whether it's surface or deep underground, at some point you often need to break up solid rock. That brings us to the controlled power of drilling and blasting.
Exactly. Drill and blast is still a very common, very effective excavation method for all sorts of rock, both surface and underground. Often has a lower initial cost compared to purely mechanical methods like tunnel boring machines or giant excavators.
Can you walk us through the typical steps in a blasting operation? The cycle again?
Sure. It starts with drilling that pattern of blast holes.
Yes.
The design number, depth, spacing is crucial, often done with multi-boom rigs called jumbos underground.
All right.
Then load the holes with explosives and detonators. Connect them all up in a specific sequence, clear the area, completely personnel, equipment, initiate the blast. The explosives detonate in sequence, often with tiny delays between holes to optimize how the rock breaks and control vibrations.
And after the bang?
Crucial step. Ventilation. Clear out the dust and harmful gases from the explosion. Then comes mucking, removing the broken rock, the muck pile, usually with loaders and trucks or conveyors. Then scaling, checking for and removing any loose rock on the new surfaces.
Safety first.
Absolutely. Then initial ground support often goes in rock bolts, maybe sprayed concrete called shotcrete. Finally, extend the utilities, ventilation ducts, power, water to the new working face, and you're ready for the next round.
So it's a highly coordinated, very safety-focused process. I also read that the pattern you drill the holes in is really important.
The drilling pattern design is absolutely critical. So many factors influence it. The size and shape of the excavation you're making, the rock properties, its strength, hardness, any natural fractures, the type and amount of explosives, if there's water in the holes, any limits on ground vibrations or air blast, the drilling equipment you have.
Wow, lots to consider.
Yeah. The goal is to place the explosives perfectly to fracture the rock efficiently, get the right fragment size for easy removal, but minimize overbreak damage to the rock you want to leave behind, and minimize disturbance to the surroundings.
Now let's talk about the explosives themselves. I know there are different kinds, different levels of power.
Right. Blasting basically relies on the rapid energy release from an explosive to fracture rock. We generally categorize them by reaction speed. Low explosives deflagrate, they burn very fast, subsonically, producing gas, but no real shockwave. Black powder is the classic example.
Okay.
High explosives detonate. That's a rapid supersonic chemical reaction generating a high-pressure shockwave that shatters rock. Dynamite is a well-known one.
And they're classified further?
Yes, by sensitivity. Primary explosives are very sensitive, used in detonators to set off less sensitive ones. Secondary explosives can burn, but need a primary explosive to detonate properly. Tertiary explosives are even less sensitive, need a significant energy boost, usually from a secondary explosive, to detonate.
So it's a controlled chain reaction. What are common ones used today?
Common tertiary explosives in mining are ANFO, that's ammonium nitrate fuel oil, and various water-based explosives like slurries and emulsions. They're generally safer to handle.
I also came across controlled blasting. What's that about? Is it different?
Controlled blasting techniques aim to minimize damage to the rock beyond the intended excavation line and control vibrations and air blast. Critical near cities or sensitive areas.
How do they do that?
Specialized drilling patterns, often reduced explosive charges in the holes right at the edge. Techniques like pre-splitting, where you fire a line of closely spaced holes before the main blast to create a clean fracture plane. Trim or cushion blasting also uses lightly loaded perimeter holes for a smoother final wall. Smooth blasting is another term for getting a clean, stable surface.
And if you can't use explosives at all?
In some sensitive situations, yeah, you might use non-explosive methods like expansion chemicals poured into boreholes. They expand and crack the rock. But it's often slower and needs a lot of drilling.
Okay, so the rock is broken, it's brought to the surface or out of the tunnel, but it's not pure metal or mineral at that point, is it? There's a whole process of separating the valuable stuff from the waste rock.
Exactly right. The raw mine material, the run-of-mine ore, is a mix of the valuable minerals and unwanted rock and minerals called gangue. Or processing, or mineral beneficiation, is the series of physical and chemical processes used to separate the valuables from the gangue, concentrating them into a more usable form.
And there are some key terms we should probably know for this stage.
Yes, definitely. The head, or feed, is the raw ore going into the processing plant. The concentrate is the valuable product coming out, enriched in the mineral you want. The tailing, or tailings, is the waste material left behind.
Okay, head, concentrate, tailings. What about middlings?
Middlings are particles that are kind of halfway there. They contain both valuable minerals and gangue. They often need more processing to get full separation. And a key metric is recovery, the percentage of the valuable metal in the original ore that actually ends up in the final concentrate. Higher recovery means a more efficient process.
So the goal is maximum recovery, minimum waste. What are the main physical methods used to separate things?
Several methods exploit differences in physical properties. Sometimes optical or radioactive sorting can work, picking out particles based on appearance or radiation. Gravity separation uses density differences. Think of shaking a pan, heavier stuff settles. Concentrating tables use water flow to separate denser minerals from lighter gangue.
Right.
Froth flotation is a huge one, very widely used. It exploits differences in surface properties. You grind the ore finely, mix it with water to make a pulp or slurry, then add chemical reagents.
What do the reagents do?
Some make the valuable mineral particles hydrophobic, water-repelling, so they attach to air bubbles blown into the pulp. These mineral-laden bubbles rise to the surface as a froth, which gets skimmed off, leaving the gangue minerals, which are hydrophilic, water-attracting, behind.
Clever. Like attracting the good stuff to bubbles.
Basically, yeah. For example, sodium ethyl xanthate is a common collector used for floating galena, which is lead sulfide. Then there's magnetic separation for magnetic minerals like magnetite using powerful magnets. Weatherill's magnetic separator is a type of machine for that. And electrostatic separation uses differences in electrical conductivity. Separates conductors like cassiterite from non-conductors like zircon by passing them through an electrostatic field.
That's a fascinating array of physical tricks. Are there also chemical recovery methods involved?
Yes, dissolution is a chemical method. For instance, you can leach or dissolve copper and iron from ores like malachite using sulfuric acid and an oxidizer. Then you recover the metals from the solution chemically.
And I saw some pre-treatment processes mentioned like drying, calcination, roasting. What role do those play?
Those prepare the ore or concentrate for later stages. Drying just removes moisture. Calcination heats the material to decompose it, removing things like CO2 from carbonates or water from hydrated minerals. Roasting is a high-temp process, usually oxidizing sulfide minerals into oxides, which are easier to process later, and releasing sulfur dioxide gas. Copper sulfides often get roasted before smelting.
Okay, getting it ready. What about agglomeration?
Agglomeration techniques, sintering, pelletizing, briquetting, nodulizing, take fine particles and clump them into larger, stronger lumps. This makes them suitable for processes like blast furnace smelting, where fine powder would just blow away.
And heap leaching. That sounds different.
Heap leaching is important, especially for gold and copper from low-grade ores. You crush the ore, pile it in large heaps on an impermeable pad, then sprinkle the leaching solution like dilute cyanide for gold over the top. It percolates down, dissolving the metals. The metal-rich solution collects at the bottom for processing.
And smelting. That's about heat, right?
Yes, smelting is a high-temperature process, pyrometallurgy, used to extract a base metal from its ore by melting it and separating it from impurities, which form a molten waste layer called slag.
So it's often a really complex multi-stage journey from raw ore to a usable concentrate. And with all this mining and processing, there must be a significant amount of waste generated. How is that managed responsibly?
Mine waste management is an absolutely critical aspect of modern mining. Hugely important environmentally and economically. There are several different types of waste produced.
Like what?
Overburden, the stuff removed to get to the ore. Waste rock, which has some minerals but not enough to be economic right now. Tailings, the finely ground waste from processing. Slags, the byproduct from smelting. Mine water that collects in pits and workings. Water treatment sludge from cleaning that water. And even gaseous wastes like dust and sulfur oxides.
That's a wide range of waste products, each with its own potential risks, I imagine.
Indeed. A major environmental concern, especially with waste rock and tailings containing sulfide minerals, is acid rock drainage, ARD. When those sulfides meet air and water, they react to form sulfuric acid, which can then leach heavy metals and other toxins into water systems.
That sounds bad.
It can be very bad. So careful, comprehensive waste management is essential. Proper containment in engineered facilities like tailings dams, treating contaminated water, responsible disposal. Modern mines increasingly prioritize this, incorporating waste management into the design from day one, including planning for eventual site reclamation.
It's good to hear that planning for the end is part of the beginning now. What about the possibility of turning some of this waste into a resource itself? Is that happening?
Yes, there's a growing recognition of that potential. Reevaluating waste streams as secondary resources. Maybe waste rock deemed uneconomic before becomes viable with new tech or higher metal prices.
Interesting.
Tailings are sometimes used in agroforestry as soil amendments, or in construction materials like bricks and cement. Slag can be used as aggregate for roads or in concrete. Mine water can be treated and reused. Even sulfur oxide emissions can be captured and turned into sulfuric acid, which is valuable.
So closing the loop somewhat.
Trying to, yeah. And after closure, waste management continues long-term monitoring of storage facilities, making sure they're stable, preventing leaks, and reclaiming the land, restoring it to a productive or natural state.
All this activity sounds inherently hazardous, though. What about the crucial aspect of safety for the people working in these mines and for the surrounding environment?
Ensuring safety and occupational health is an absolute top priority. It has to be. This covers promoting workers' physical and mental well-being, ensuring their working capacity, and creating a safe, healthy working environment. Unfortunately, the International Labor Organization, the ILO, estimates the mining sector still sees significant numbers of accidents, diseases, and fatalities globally each year. It highlights the ongoing need for rigorous safety protocols and continuous improvement.
What are some of the key areas of focus for mine safety?
Fire safety is a big one, especially in underground coal mines. That means risk assessments, identifying hazards like flammable gas, fire damp, coal dust, potential ignition sources, friction, sparks, electrical faults, then implementing controls, minimizing fuel and ignition sources, using fire-resistant materials, fire dam drainage systems, regular inspections, fire alarms, extinguishers, clear evacuation plans that are practiced regularly.
Ventilation must be critical, too.
Absolutely critical underground. Removing toxic and explosive gases, dust, fumes, and supplying continuous fresh air to all workings. And adequate lighting, both portable lamps for miners and fixed lighting, is crucial for preventing accidents and just being able to work effectively.
Sounds like a constant battle against potential hazards, requiring ongoing vigilance and engineering. Finally, let's step back and look at the bigger picture. How does this whole mineral industry connect back to the fundamental science of geology?
Well, mining geology is essentially the bridge. It connects economic geology, the science studying how and where mineral deposits form, with mining engineering, the practice of safely and efficiently extracting those resources. Mining geologists and engineers work hand in hand throughout a mine's life.
From start to finish.
From exploration and resource evaluation, through mine design, operation, and closure. Remember, a mineral has a specific scientific definition. Naturally occurring, solid, inorganic, definite chemical composition, characteristic crystalline structure.
Got it.
We broadly classify them into metallic minerals containing metals like iron, ferrous, or copper, gold, non-ferrous, and non-metallic minerals like clays, gemstones, quartz. An ore mineral is one you can economically extract something valuable from, unlike the gangue minerals, which are the waste associated with it. Ore itself is the mix of ore minerals and gangue mine.
So geology tells you what's there and where, and that informs how you get it out. And the mineral industry has really been a cornerstone of human civilization's progress, hasn't it?
Oh, absolutely. Think about it, Stone Age, Bronze Age, Iron Age, right up to today's tech. Minerals have always been the essential raw materials driving advancement, economic growth, society. A modern mineral industry needs significant infrastructure material handling, transport networks, environmental treatment facilities, power, admin buildings.
Yeah, this whole ecosystem.
Exactly. Minerals feed countless basic industries: construction, manufacturing, electronics, agriculture. Quality control is vital. Economics are driven by supply and demand, so market studies are crucial. And beyond metals, there's a huge range of other mined materials. Industrial minerals for construction, ceramics, chemicals, gemstones, dimension stones like granite and marble, basic construction aggregates, fuel minerals like coal and oil, radioactive minerals like uranium, even geothermal resources.
Right.
Our sources even gave specific examples like marble in Godavari, coal in Dang, radioactive minerals in Mustang, dimension stones in various districts, river boulders used for construction. It highlights the diverse geology and resources within just one region.
It's truly remarkable when you think about it, this intricate web of geological knowledge, engineering ingenuity, economic calculations, and that constant focus on safety, all coming together to extract the raw materials that, well, underpin our entire modern lives.
It really is. What might seem like just digging a hole is actually a highly sophisticated, interconnected system. It involves numerous scientific and engineering disciplines, it's driven by economics, and there's an ever-increasing focus on environmental responsibility and long-term sustainability.
So the next time you use pretty much anything, whether it's the device you're listening to this on, the vehicle you drive, the buildings around you, maybe take a moment to think about the incredible journey of the raw materials that went into it, the many different minerals, the complex and fascinating processes we've just explored in this deep dive. What further questions does this exploration spark for you about the future? About how we extract and utilize Earth's mineral wealth in a truly responsible and sustainable way going forward?